Okay, see here in combustion, it is such an important factor. Why? Because depending on the combustion, okay, the major work done and all are going to differ. Okay, if we have complete combustion and we are going to maintain complete combustion, okay, so to maintain complete combustion, we need to check several parameters like how the pressure and temperature are going to develop within an engine, okay, and how much fuel air mixture is going to be there. Okay, if there is a proper mixing of fuel and air is there or not. Okay, if there is improper mixing, then there will be incomplete combustion is going to be there. Okay, so to our main motto is to have higher pressure and temperature. Okay, whatever is the maximum possible pressure and temperature is there, that much amount of pressure and temperature should be created to have a complete combustion. Okay, for that we need to check several parameters like airfield mixture. Okay, how the air and fuel are going to mix. Okay, if the air and fuel is not going to mix well, okay, their proportions are going to be good. Okay, and we also do the air fuel ratio also. Okay, according to the engine speed, this air fuel ratio has to be supplied in a quantitative manner and also in a qualitative manner. Okay, we need to check the properties of fuel also. Okay, it should have some anti-knock characteristics. Okay, so if we are going to face anti-knock characteristics, then we may be have that means we may be having some high pressure and temperature rates, so that complete combustion is going to be there. Okay, so I will discuss knocking after discussing how the combustion is going to happen in IC engines. After that I will discuss how during combustion the knocking is going to be there. Okay, first of all I will discuss combustion in SI engines, and after its knocking. Okay, and what are the parameters we need to limit the knock. Okay, and how this combustion is going to have several stages. Okay, and after that we are going to move to combustion in CI engines, and combustion in and also knocking in CI engines. Okay, there will be two different types of knocks will be there. Okay, knocking in SI engine is different and knocking in CI engines is going to be different. Okay, we will discuss the differences in knockings in SI engines as well as in CI engines like that. Okay, so and we need to know first of all to know combustion. Okay, first of all we need to know what are the parameters which are going to affect the combustion. Okay, what is the properties need to be required, okay, to have a complete combustion. Okay, so theoretically there will be one process, and practically it is going to be it is not going to be the same. Okay, why? Because theoretically what we have till now what we have discussed, theoretically the combustion is going to be exactly at the top dead center. Okay, but practically when in actual cycles what is going to be there, it is not going to be exactly at the top dead center. We need to advance the spark. Okay, during the timeless factors I have discussed this with you. We are going to have progressive combustion in case of actual engines. Okay, so we are going to have time loss factor in case of actual engines, and because of this we are going to have effect on the combustion process. Okay, see, if we have during the discussion of time loss factor we have discussed the spark advance, right? In spark advance what we have did, we have an optimum condition where we need to ignite the spark. Okay, so some around 15 to 30 degrees before, in between, we are going to initiate the spark to have maximum pressure and temperature. Okay, if the pressure and temperature are maximum, then we have chances of getting complete combustion. Okay, so otherwise if the spark is too early, that is around 40 to 50 degrees before TDC only. Okay, before 40 to 50 degrees TDC, we are then also we are going to have losses. So we need to follow some optimum condition for spark ignition. Okay, so similarly to have a complete combustion in actual cycles, we are going to follow that spark advance. Okay, optimum condition in spark advance. Okay, so completely so it is such an important factor, combustion. Okay, why? Because the combustion is going to play a major role in deciding the maximum pressure and temperature attained in the cycle, and also peak the mean temperature and mean pressures are going to be achieved in the cycle, and also we are going to have 1 minute, please. Okay, at the same time we are going to have some losses here. Okay, because of if the pressure and temperature are not appropriate, okay, if there is no incomplete combustion, the pressure and temperature evolved are not that to actual extent. Okay, so that's why it is going to affect several factors. Okay, so see here, first of all, what is combustion? Okay, combustion is nothing but to have a combustion. Okay, there will be combustion in both SI and CI engines. Okay, first of all, talking about combustion, okay, in general way, combustion is nothing but mixing of fuel and air, and after proper mixing of fuel and air, okay, we are going to give some spark to it. Okay, whenever we have given spark to it, then there may be some explosion is going to be happen there. Okay, that is actually the combustion. Okay, see here, air and fuel means here fuel, what we are going to have some hydrogen and carbon particles. Okay, and also several particles will be there. Okay, fuel, for suppose if we take petrol or diesel, both are nothing but the compounds of hydrocarbons. Okay, when these hydrocarbons like HC mix with the air, what are the components of air? Nothing but air consisting of oxygen, nitrogen, sulfur, and all several organic gases also will be there. Okay, but majorly we are going to have nitrogen and oxygen. Okay, when this nitrogen and oxygen in air mix with the fuel, okay, like HC, fuel mainly consisting of hydrocarbons like HC, when they are mixing with oxygen, HC plus O2, okay, or N2. Okay, Hc plus O2 plus N2 gives rise to CO2, H2O, all those parameters we are going to get. Okay, after combustion, okay, after reaching, okay, first of all there will be some mixing, proper mixing will be there, and after that we are going to compress them. Okay, so to attain some pressure and temperature for the mixture. Okay, so to have some pressure and temperature, otherwise at normal conditions they are not going to ignite. Okay, so at a normal conditions, since they are not going to ignite, we need to increase the pressure and temperature for that air fuel mixture. Okay, whenever there is a high pressure and temperature for that air fuel mixture, okay, then only it is going to ignite, otherwise it won't ignite. At normal atmospheric conditions, when these two are going to mix, okay, without any spark, they are not going to ignite. Okay, so with a minimum spark possible, okay, we have given to ignite that at a high, we need to take them to higher pressure and temperature, and then the combustion is going to be effective. Okay, so after that, whatever the combustion gases are there, okay, they are able to do some work. Okay, like the whatever the energy is going to liberate, okay, there is some energy is going to liberate after the combustion. Okay, this energy, whatever the energy is developed or liberated, that liberated combustion gases are going to do some work on the piston. Okay, so because based on that work, they are that energy liberated is possible, is making possible the piston to move downwards, otherwise it can't do some work. Okay, it will combust only. Okay, so to do some work, there must be some high pressure and temperature for the combusted gases. Okay, so that's why here fuel and oxygen from air, okay, when they are mixed, and after that we have supplied heat. Okay, heat supply means nothing but initiating a spark. Okay, so after that we are going to have exhaust gases, and these exhaust gases may contain CO2, CO, N2O, like water, H2O. Okay, and some nitrogen, ammonia, like that also may be possible. Okay, uh, and some heat is going to be generated. Okay, so this is how combustion is going to happen. See here somewhat oxygen is there, fuel is there, and heat is also needed to have complete combustion. Okay, so that is what combustion means. Okay, in IC engines we are going to have chemical energy. Chemical energy means nothing but whatever the hydrocarbons are there within the fuel. Okay, and when they are going to mix with air, whenever, and in addition to that, if we supplied heat to that, okay, if we supplied heat to that, for the chemical energy which is going to be there in the Airfield mixture. Okay, that means here heat means initiation of spark with the help of spark plug. If it is SI engine, okay, spark ignition. If it is CA engine, there may be self ignition temperatures and compression ratio is going to be high. Okay, so because of having high compression ratios in case of CA engines, okay, they may self ignite. Okay, because of because of certain high pressure, if the compression ratio high, the more amount of pressure and temperatures are going to be there within the mixture of air and fuel. Okay, so that's why there may be some chemical energy. When it mixes with heat, we are going to get some mechanical energy. Okay, mechanical, that means we are going to transform the chemical energy to mechanical energy, and after that we can use to several purposes. Okay, and that means we can also generate some electrical energy. Okay, so that is the uh, main motto using IC engines. Okay, we not only restrict, if it is bikes or something, then we can stop with mechanical energy only. Okay, so for suppose if we need to generate some an electrical energy, then we need to convert it mechanical energy into electrical energy. Okay, so that is the use of internal combustion engine, which is going, how the combustion or chemical energy is going to transform into mechanical energy in case of automobiles and electrical energy in case of power plants. Okay, so here see, in chemical energy is going to transform into radiant energy, light. Okay, light means nothing but there will be some spark, some light is going to be generated. Okay, and some thermal energy, nothing but heat energy. Okay, some heat and light will be there after combustion. Okay, so here combustion is nothing but transformation of chemical energy into light and heat energy. Nothing but light means here radiant energy, and heat means nothing but thermal energy. Okay, so this chemical energy after combustion is going to transform from light energy and heat energy, nothing, in other words, radiant energy and thermal energy. Okay, that is the combustion. Okay, see here, combustion, coming to combustion in SI engines. Okay, it is nothing but a chemical reaction in which certain elements of the fuel like hydrogen and carbon, I already explained this to you. Okay, how combustion is going to happen. Okay, combustion is nothing but a chemical reaction or chemical process when fuel, we are going to have fuel and air, when these are going to mix. Okay, in fuel we are going to have hydrocarbons. Okay, this is the structure of gasoline, like C18H18. Okay, and this is diesel. Okay, this is for CI engines. Okay, here the diesel molecular structure is C14H30. Okay, so the molecular structure of diesel is like this. Okay, mostly it is going to be like this, and its chemical formula is C14H30. Okay, so HC carbons mostly we are going to have. See, HC carbons, as I already said, there will be some HC hydrocarbons like C14H30. And here also in petrol, gasoline means nothing but petrol. Okay, in petrol we are going to have C8H18. Okay, so whenever they mix with air, air means nothing but oxygen. Okay, so this HC hydrocarbons mix with oxygen, so HC means C8H18 means nothing but fuel here, gasoline. Okay, and when it comes to mix with oxygen, that means nothing but air. Okay, so fuel and air mixing like that. Here C18H18 is the fuel, which is hydrocarbons, and O2. Okay, majorly we are going to have O2, so that's why he given O2 here. So see how the chemical reaction after combustion is going to be there. We are going to have some carbon dioxide, O2, if it is complete combustion. Okay, if it is incomplete combustion, we may have CO. Okay, carbon monoxide. And if we have in air, there may be nitrogen also. Okay, so if we have nitrogen, then we are going to have carbon monoxide, nitrogen oxide, and water also. Okay, in addition to that, we are going to have some heat energy also. Okay, whenever there is combustion is going to happen, whenever they have mixed, and if we have initiated a spark, there may be some combustion, and after that there may be these components. These are the combustion gases. Okay, and in air there may be sulfur also. Okay, so if we have taken sulfur also, then the reaction is going to be somewhat bigger, and which is not to much extent which is an important thing. Okay, the mixing of oxygen and nitrogen is sufficient to analyze it. Okay, and there may be some liberation of heat is also will be there. Okay, see the Carbons in case of gasoline are going to be like this. Okay, whatever the round balls with the black are there, those are going to be the carbon compounds. Okay, these are carbon particles. Okay, these are carbon atoms, and in green they are the hydrogen atoms. Okay, these are the hydrogen, whatever the green are there. So in this chemical way they are going to be in mix. Okay, in this chemical form they are going to be in mix in case of, if we take petrol or gasoline. Okay, and if we take diesel, okay, the molecular structure is going to be like this. Okay, and for molecular structure for petrol is going to be like this. Okay, consisting of some hydrocarbons, nothing but C8 H18 is here, and in case of diesel it is going to be C14 H30. Okay, and whenever there is some mixing, those are going to mix with each other. That means of fuel and air, and there may be some initiation of spark. Okay, why we need to initiate spark here? Because there may not get some self ignition temperature. Okay, to have some combustion we need to initiate a spark, and after that there may be combustion, and these are the combustion products which are going to be evolved in after combustion. Okay, and this we call them as exhaust gases or combustion products. Okay, and we can call them as the emissions also. Okay, if there is incomplete combustion, the emissions are going to be high. Okay, there may be some black ash and soot also will be there. Okay, so that's why we need to maintain proper combustion, complete combustion. Okay, then only we may achieve higher pressure and temperature, and mean effective pressures, okay, is going to be high. Okay, so that the work done and efficiency are going to be high. Okay, so see here, we are going to have two types of mixtures. Okay, I already said this to you. Okay, one is homogeneous mixture and heterogeneous mixture. Okay, what is homogeneous mixture and where we are going to find the homogeneous mixture? Okay, I already said this to you, and again I am going to tell you this. Okay, homogeneous mixture means before coming into the combustion chamber we are going to have pre-mixture only. Okay, before coming to the combustion chamber there is already the fuel and air are going to be mixed. Okay, this type of situation where we will see in case of SI engines. Okay, in case there will be carburetor in case of SI engines, and before getting into the combustion chamber we are going to mix the air and fuel with the help of carburetor, and after using the throttle valve. Okay, after mixing of this air and fuel in the carburetor, okay, they will flow through the throttle valve according to the speed of the engine. Okay, this throttle valve is directly connected to the accelerator. Okay, whenever we have pressed accelerator or whenever we need to raise the speed, this throttle valve is going to open here. Okay, so by the opening of throttle valve, the required amount of air fuel mixture is going to be taken into the combustion chamber for combustion. Okay, see here, if it is homogeneous mixture, that means if it is properly combined, okay, then we are going to have some complete combustion here. Okay, see here, if it is homogeneous mixture, the molecules are going to be mixed like this. Okay, so if it is a heterogeneous mixture means what? Okay, after pressurizing the air, okay, that means within the combustion chamber we are going to mix air and fuel, that is heterogeneous mixture. Okay, so there may be, because of less span of time available, they are not going to mix well. Okay, like this. Okay, if it is homogeneous mixture, see how the molecules are going to be in a proper mixing. See, they are mixed very properly. But if it is heterogeneous mixture, okay, they are going to be as part only, but after some time they will become like this. Okay, at the start of the combustion they are not going to mix equally in equal proportions like this, but they will mix after some time, and because of that only we are going to have combustion. Okay, if they have not mixed properly, okay, then there may be no complete combustion. And where we see the heterogeneous mixture, in case of CA engines, that means compression ignition engines, we are going to have heterogeneous mixtures. Okay, so in case of CA engines we are going to have some air. Okay, first of all we are going to take air through the inlet, and during that suction process, okay, this whole air is going to be sucked in, and during compression process what is going to be done, the whole air is going to be compressed. Okay, so if we compress the air, that means nothing but pressure and temperature are going to increase here. Okay, after the whole pressure and temperature increases. Okay, if pressure and temperature increases, automatically the density also increases. Okay, if there is increase in density, that means if we have more density, okay, more dispersion is going to be done. Okay, if we have less density, okay, the dispersion is not going to be proper. Okay, if we have more density, okay, the whole fuel which is injected at the end of compression stroke is going to mix well with this air. Okay, otherwise the density is less. Okay, if the density is less, what happens is, okay, whatever the fuel is there, they will travel throughout the air and will contact the combustion chamber and piston head. Okay, so if it is going to contact, if the fuel is going to touch the cylinder walls and the piston head, then it is not helpful for the combustion. Okay, so they may touch these walls and piston head, and there may be wastage of fuel will be there. So if wastage of fuel is there, okay, we are going to send only the amount which is required. Okay, the amount of fuel which is required only we are going to send. Okay, so if it is lost in a piston head and cylinder walls, what happens, there may be no sufficient fuel for the complete combustion. Okay, so that's why we need to maintain high density for the air which is going to be there. Okay, that means we need to increase pressure and temperature as much as possible. Okay, so if we have more pressure and temperature, the density is going to high, so there may be some more dispersion within the air only. Otherwise they will, if the dispersion is more, that means if the density is less, dispersion is going to be more. Okay, that means it is going to travel throughout the air and will touch the cylinder walls, which is not advantageous. Okay, so we need to see that. And this is because of improper mixing. Okay, we need to advance this part. That means we need to have fuel injection before it reaches TDC only. Okay, so that when the piston reaches TDC, there may be some complete mixing of it, and because of some high pressures developed here, okay, by mixing of air and fuel, there may be some self ignition temperature is going to reach, and in CI engines, and then there will be combustion is going to happen. Okay, so because of mixtures also, we are going to have different types of combustions here. Okay, so if it is homogeneous mixture, we are going to have one type of combustion, and if it is heterogeneous mixture, we are going to have some other type of combustion. Okay, so here main importantly, if it is homogeneous mixture, okay, we will use this in SI engines, and heterogeneous mixture which is going to be used in CI engines. Okay, and because of this, the losses are going to be very few. Okay, mainly due to incomplete combustion only we are going to face losses in case of CI engines. I already discussed this in last class also. Okay, forget about that. I hope you got that idea where the losses are going to, why the losses are going to be minimum in case of CI engines when compared to SI engines. Okay, here only due to incomplete combustion is going to be the major loss. Okay, in case of CI engines, but here we are going to face several losses. Okay, so because of that losses, the efficiency is going to be low when compared to CI engine. Okay, that is homogeneous mixture. The mixture components are distributed uniformly here, and here there is no such uniformity in case of heterogeneous mixture. Why? Because there is no much time available for air and fuel to mix properly. Okay, so that's why they are going to be like this. Okay, but after some time they will definitely mix with each other, and after that mixing only we are going to have combustion. Otherwise there will be no combustion. Why? Because if there is no proper mixing, it can't reach self ignition temperature. Okay, after having some proper combustion, that means after having proper mixing only, that may reach, that means hydrocarbons like HC, and mix with the oxygen and nitrogen within the air properly, and after that we are going to have combustion. Okay, so that's all about homogeneous mixture and heterogeneous mixture. And a homogeneous mixture, here we need to talk about stoichiometric mixture. Okay, what is stoichiometric mixture? And the equivalence ratio. Okay, stoichiometric mixture is nothing but to burn the fuel, 1 kg of fuel completely, we need a certain amount of air. Okay, majorly we will take 1:15 ratio. That means 1 kg of fuel is to 15 kg of fuel. Okay, so that is the stoichiometric mixture. Okay, and what is equivalence ratio? Okay, equivalence ratio is nothing but actual air fuel ratio by stoichiometric air fuel ratio. Okay, what is actual air fuel ratio? It depends upon the engine speed. Okay, depending upon the engine speed, we need to take required amount of air fuel mixture. Okay, so if we are going to maintain the engine speed at high pressure, high speeds, okay, then we need to have rich mixture. That means actual mixture. Okay, fuel air fuel ratio is going to be high. That means we are going to have more amount of fuel here. Okay, so if the more amount of fuel is there in actual mixture, 1 is to 17 like that, sorry, 1 is to 12 like that is going to be there. Okay, 1 is to 12 by 1 is to 15. Okay, which is stoichiometric mixture. Then we are going to have the equivalence ratio, 1 is to 15 by 1 is to 1 is to 14 by 1 is to 15. How much? Depending if the 5, that means equivalence ratio is going to be denoted with 5. Okay, 5, you know 5, right? 5 is equal to actual air fuel ratio by stoichiometric air fuel ratio, like 1 is to 17 is to 1 is to 15. Okay, so finally we are going to get 15 by 17. Okay, which is going, it is going to be some lean mixture, right? Okay, so the now the equivalence ratio is less than 1. Okay, so if it is less than 1, there may be some incomplete combustion will be there. Why? Because it is not going to get some high pressure and temperature. Okay, if this equivalence ratio 5 is greater than 1, like 1.1 to 1.2. Okay, 1.1 to 1.2 in case of homogeneous mixture. In case of SI engines, we need to maintain the 5 as 1.1 to 1.2. Okay, if it is the if the range is like that, then we are, that means a somewhat rich mixture if we send. Okay, somewhat a rich mixture if we send, then we are going to have proper combustion or complete combustion. That means it is the accurate value to have complete combustion. Okay, and if it is heterogeneous mixture, okay, the equivalence ratio should be around 1.1 to 1.2, 1 to 1.2. Okay, why? Because here we are going to have local zones. Okay, and it will reach here we are going to maintain high compression ratio. Okay, here the compression ratio is around 16 to 20, but here in case of SI engines it is only 6 to 10. Okay, because of high compression ratio, okay, the pressure and temperature attained are very high. Okay, around 70-80 bar will be like that. Temperatures are also some around 600 Kelvin, 700 Kelvin, like the temperatures we are going to have. Almost 2000 Kelvin is going to reach at the end of combustion. Okay, at the start of combustion it is around 600 to 700 only. Okay, so if we have the equivalence ratio, that means if we maintain some rich mixtures. Okay, if we have some rich mixtures, that means a rich amount of fuel is there, and we are going to reduce the air quantity. Okay, we are going to increase the fuel quantity. Okay, then the equivalence ratio is going to be somewhat 1 is to 1.1 to 1.3, 1.2 1 to 1.2 will be there in case of heterogeneous mixture we need to maintain. Okay, to have complete combustion. Here 1.1 to 1.2, and here 1 to 1.2. Okay, those are the somewhat rich mixtures. Okay, here most stoichiometric also will do the complete combustion here. Okay, stoichiometric equivalence ratio is 1, means nothing but stoichiometric and actual air fuel ratio are going to be the same, 1 is to 15 by 1 is to 15. Okay, so that's why we are going to have equivalence ratio as 1. Okay, so that we can have complete combustion here if it is heterogeneous. Okay, if it is homogeneous, 1 is to 15 by 1 is to 15 is not appropriate. Why? Because certain high pressure and temperatures are not going to reach because of low compression ratios. Here we are going to maintain only 6 to 10 compression ratio. Okay, so such high pressure and temperature are not going to attain. So we need to take some rich mixture to have complete combustion. Okay, so that is about equivalence ratio here. Okay, next coming to combustion in SI engines. Okay, see here, in case of SI engines, okay, what I said, the combustion in SI engines and CI engines is going to be different, not at all. That means nothing the same. Okay, the process, the combustion progress in case of SI engines is one type, and the combustion progress in CI engines is another type. Okay, there are different types are going to be there in case of combustion of SI engines and CI engines. So we need to learn combustion in SI engines and CI engines separately. Okay, so first of all we will go through the combustion in SI engines, and after that we will know what is actually combustion